Yes, hello, my name is SHAUN Fitzgerald. I'm the Director of the Centre for Climate Repair at the University of Cambridge. My interest in climate started actually when I was an undergraduate here at the University of Cambridge. I read engineering, and back in the late 80s I got the energy bug. I don't know why, but realised that fossil fuels as a source of energy was doing terrible things to the environment, and therefore I went on a trip at the end of my second year around the United States of America for about 6 weeks, and we visited a whole raft of different, what they then called alternative energy installations, so tidal, solar, wind, biomass, geothermal, hot dry rock. And I realised that actually there were ways that we could provide energy for society without releasing fossil fuel carbon dioxide. So I then got into the world of geothermal and did a PhD, and I joined the faculty at Stanford later on, running the geothermal program. And then marched forward 20 odd years in the world of emissions reduction, which is largely what geothermal is, as a way of providing energy without fossil fuels and the release of carbon dioxide. We can also use less energy in the first place through energy efficiency measures, such as energy efficient ventilation in buildings, both of which I have done. But unfortunately, society has continued to increase its rate of releasing emissions to the environment, and therefore we need to do more, and that's why I've come back to the University of Cambridge to be with the Centre for Climate Repair.
How did the centre come about? Can you just give us a bit of a background on the centre?
Well, the centre was the brainchild of Sir David King, a previous government chief scientific advisor to the United Kingdom, and it was established in 2019, originally based at Downing College. And it came about because Dave really realised that, in fact, we were not going to just be able to path our way forwards just with emissions reduction. We needed to continue very, very strongly on the emissions reduction pathway. But we need to do more than that, and therefore set up the Centre for Climate Repair to A, start with emissions reduction, but B, also look at ways that we can really scale up greenhouse gas removal. That's recognising that greenhouse gases are already at a level that's too high in the atmosphere. So we've got to bring those down. And then lastly, we call it refreeze, but looking at also approaches that we might need in the future in order to buy time to get greenhouse gas levels down without losing, for example, all of the ice on Antarctica or all of the ice on Greenland, with the concomitant sea level rise and the devastation that would wreak upon society at large.
I just want to use this somewhere else. Can you just give me a short sound bite on reduce, remove and refreeze?
So the strategy for climate repair is indeed the 3 R's that we call reducing emissions, but also removing greenhouse gases that are already in the atmosphere, and the third that we term refreeze, which is buying time to make sure that we got ice being kept on Antarctica, ice being kept on Greenland, whilst we get greenhouse gas levels down. It's the 3 R's.
And then can you just add to that the evaluation process that you referred to, the EAO2 CDR?
So in all of these approaches of emissions reduction, greenhouse gas removal and refreeze, there are a whole portfolio of different approaches that are going to be possible. But for each of these 3 R's, we look at ones which are, first of all, going to be scalable. So can you actually scale them up in a reasonable time frame to make a difference? They've got to be meaningful. And in terms of greenhouse gas removal, one of the metrics we use is if we really can't get to something like a gigaton of carbon dioxide or carbon dioxide equivalent per annum, then actually go and look somewhere else. So it's got to be meaningful, but it's also got to be acceptable to wider society, and it also has to be something that is affordable. So it's got to be economically sensible for society to bear.
I'm just going to stay on this line actually, because okay, recording.
So when I say socially acceptable, I mean we need to think very hard about what we mean by society at large. And it is the people who are going to be most affected by the effects of climate change and who are going to be least able to adapt and afford to adapt that we need to not just bring into the room, they need to be significant decision makers in terms of helping map our way forwards. So I often get asked, are you engaging with the local stakeholders? And I like to say the answer is no. And the reason being is if you're just asking for engagement with local stakeholders, then you're shooting way too low. Your ambitions need to be much, much higher. I think we need to be not just engaging, we need to be involving, and ideally also being led by some of these peoples, because when we are looking at, for example, things like seabed curtains, that will affect glaciers in Antarctica, glaciers in Greenland perhaps, as a potential intervention. Who are the people that we should be asking for advice on whether this is a sensible thing to go forwards with? It's not just people in the United Kingdom. I had this most wonderful opportunity to be in COP28 in Dubai, in the audience with a lady speaking who was the United Nations ambassador to the islands of Palau. They're a group of atolls in the South Pacific. An incredibly eloquent speech where she said, for my people, 1 or 2 meters of sea level rise is not a case of losing a bit of beach. It is a case of losing our country. And for people like this, they need to have a very significant seat at the table in terms of determining our, first of all, research pathway in terms of the technologies that we might be developing. And then secondly, actually also looking at then potential deployment.
That's great, thanks. I just want to move on to some of the... Sometimes we're held back by our experience instead of being moved forward by it, and just the... sometimes you have to be imaginative, and to me, your idea of a 62-mile barrier for the Thwaites Glacier it sounds exotic, and so can you just talk about the fact that we're in extraordinary times, we need to come up with extraordinary solutions that are obviously backed by research, but yeah, just address some of the things like that.
This concept of erecting a barrier at the bottom of the seafloor to try and reduce the rate of ingress of warm saline water to the grounding line of some glaciers is an interesting one. But in terms of just the scale involved, for example, tackling something like the Thwaites Glacier, it's 100 kilometers that we're talking about. That is incredible in terms of what would be involved working in that incredibly hostile, harsh environment. But as a concept, it's something that I do think we should be looking at this quite seriously, because if we can hold the Doomsday Glacier at bay whilst we get greenhouse gas levels down, I think quite a few people will be very interested in this. But rather than just saying, right, what is that barrier? What could it be? The first thing I ever heard about this was somebody was proposing a concrete barrier. And then more recently, people have been looking at actually a more flexible curtain, which is a flexible curtain tethered to the bottom of the ocean floor with some buoyancy aids, then just rising 100 meters from the ocean floor to reduce the rate of ingress of warm saline water to the base of the glacier. But in fact, we're now looking at things that may not even be a physical barrier. We can look at other parts of society, other engineering ideas that we deploy and learn from those. So for example, if you walk into a retail store in the height of the summer, it's roasting hot outside, it's air conditioned inside. Well, why have they got the doors open? They've got the doors open because that's a retail strategy to increase footfall, and therefore that's what drives the economy for the retail outlets. However, I don't know whether you've ever noticed, but they have an air curtain blowing air down above your head as you enter the store. So they're injecting air to try and disrupt what would be an exchange flow through the doorway, and it reduces the rate of ingress of hot air going into the interior environment. So we're going to try and learn from some other processes, and actually are we able to either introduce bubbles or introduce air flows tangential to the flows, and that would be a very different proposition than even erecting a physical barrier. So I do think ingenuity is really important, and we can look at other areas of society to try and learn from, and how might we use those ideas in new applications.
Can we go on to talk about, the concept of cloud brightening?
So cloud brightening is an interesting and potentially very helpful thing to consider for shielding more of the Earth from incoming solar radiation. So when clouds form over the ocean, they do so, let's say, in the first 1,000 meters above the sea, and those clouds provide two effects. The first is that then any sun that's shining on top of those clouds, more of it is reflected back to space rather than impacting the ocean. So they can actually protect the Earth in terms of a reflective property. The other property is that clouds also act as an insulator. So any long wave radiation, especially being radiated from the Earth, can be trapped and therefore can actually warm the Earth. So clouds provide these two fundamental processes. One helps, one hinders in terms of therefore the temperatures on the Earth. Cloud brightening is an idea whereby if you can create those clouds that were going to form anyway, but have them comprised of more smaller droplets rather than fewer larger ones, the ones that are comprised of more smaller droplets are optically whiter, and it's to do with the relationship between the size of the droplets and the wavelength of light. If they are whiter, they will reflect more of the sun's radiation. So the big question is, how might you be able to get clouds that are going to be formed of more smaller droplets? And the way to do that, potentially, is to create more sea spray. And when the sea spray evaporates, you're left behind with crystals of sodium chloride that get convected up naturally by convection currents. And those crystals of sodium chloride will act as cloud condensation nuclei. And in fact, that's how clouds form over the ocean anyway. But the game afoot, therefore, is can you create more of those cloud condensation nuclei by using sprayers in order to make the clouds ultimately whiter?
If it's appropriate, can you say that really this is kind of accelerating a natural process to a degree?
This is indeed accelerating a natural process.
Oh, I'm sorry, can you say that as a statement? Because it sounds like a response.
Oh, I see. So this, in a way, is accelerating a natural process because as the wind blows over the ocean surface, it causes white caps, that foaming, and those droplets of seawater evaporate and then get convected up naturally anyway. So what we're looking at is supplementing that, enhancing it by creating more sea spray. And so it is a natural process that we're looking at, but we need to understand also whether the size of the droplets that are going to be formed as a result of the size of the salt crystals is amenable to making those clouds whiter. The physics is really interesting. If you make the salt crystals really, 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 really small, then what happens is that, in fact, the clouds might actually evaporate. The droplets are so small, it just creates a haze, and that wouldn't help. Conversely, if the droplets that you form are quite large, then you might end up with large crystals of sodium chloride. And in fact, what you can do is form droplets that are going to be quite large, and you might cause rain out of those clouds. So it appears that there's a Goldilocks zone, that's the term that we use in the United Kingdom from an old child's story, about being not too small, not too large, just right, in order to get the clouds to form and stay there by being whiter. And that's the technology that we're looking at, is how do you generate droplets of the right size.
And at what stage is that at? Are there practical lab experiments ongoing at the moment to achieve that?
So at the moment, there are actually two field trials going on that we're aware of, and they're using a technology that doesn't appear to be generating droplets of the optimum size range, but we're learning a lot about just the physics of involving how you go and generate sea spray in a marine environment. But on top of that, there is research going on here at the University of Cambridge with a number of students and a postdoctoral researcher under the direction of Professor Hugh Hunt, looking at different techniques to generate droplets. It's been going on for about 15 months now, and the initial signs are that the first method that we're looking at is looking very encouraging. We've got 3 others being developed as well. These are radically different ideas being used to generate droplets of seawater. What we're doing is taking learnings from other industries, different applications, and saying, actually, can we use this to potentially use in the marine environment to create droplets of salt water, rather than, for example, just droplets that you might use for either inhalers or for spraying paint onto cars.
Great. So I just want to get a quick level from you.
Okay, this is Sean.
That's great, thanks. Okay, can we now talk about the pouring water on the ice project, the concept and where it's at, what the challenges are, what the possibilities are?
So one of the projects that we have ongoing at the University of Cambridge is something we called ice thickening. And it's looking at the issue with Arctic sea ice. And what's been happening is that over the last 30, 40 years, we have seen a reduction in the amount of Arctic sea ice. And specifically, the way that this is often measured is what's the amount of sea ice that occurs around September time, which is the minimum period for ice formation within the Arctic. And that minimum has been decreasing year on year for the last 30 years. And that's a real challenge, because when the Arctic Ocean is exposed, rather than it being covered with sea ice, the Arctic Ocean is a dark ocean and therefore absorbs a lot of sunlight, whereas the sea ice would be reflecting a lot of it. And given the area that's involved, and especially over the summer months, when it might not be as intense as over the equator, the sun, it's shining 24/7, and therefore when you integrate that over, let's say, a full day, you get a lot of heat being absorbed by that ocean. So what we're interested in doing is seeing whether there is a way of reversing this decrease in minimum ice extent, and at least halting it and ideally growing it. But how do we do that? Well, one of the ideas is looking at whether we might be able to get more sea ice to actually grow in the Arctic winter. And the way to do that, there are two ways that have been proposed. The first involves pumping seawater on top of sea ice and getting the freezing to occur from on top of the sea ice, rather than the freezing as would normally occur on the bottom of the sea ice. And that's because ice is a good insulator, and therefore as ice thickens, normally the rate at which new ice then forms decreases with time. So if you can overcome the resistance of the sea ice by pumping seawater on top of it, the idea being that you can create more sea ice over the Arctic winter. The second idea is also involves pumping seawater on top of sea ice, but for only limited periods of time at a given location. Because while sea ice itself is a good insulator, any snow that falls on top of the sea ice, especially in the early winter, is an even better insulator. And therefore, the other idea involves turning this snow into a solid ice layer and then allowing the overall conductivity of this matrix to be increased, and then increase the rate of formation of sea ice naturally. So those are the two big ideas, and we're supporting both of these at the moment with some numerical modelling and some laboratory experiments, and finally by actually doing some look-see experiments up in the high Arctic.
And where are you at with this? I mean, is it looking promising? What kind of feedback have you had?
The initial results that we have undertaken are actually quite encouraging. First of all, the mathematical modelling that we've done thus far indicates that both of these ideas could have serious potential. We don't know yet, but we're still in the early stages, but the initial mathematical modelling indicates that they are going to be quite helpful potentially. The second is that the laboratory experiments that we're undertaking now in the large cold room at the Department of Applied Mathematics here at the University of Cambridge, which can go down to minus 40 degrees centigrade. We're conducting a raft of different experiments at different temperatures to get a better understanding of how the freezing process, and in particular the freezing process of seawater, occurs when you put seawater on top of ice. And then thirdly, we have been out into the high Arctic under the guidance and under the leadership of an organisation called Realize. They're a not-for-profit company based in the United Kingdom and have done a magnificent job at engaging with local stakeholders, local populations, to understand whether this might be something that they would be interested in. The initial signs are most definitely that they're really interested in figuring out whether there is a way of preserving the sea ice in the Arctic, and also preserving the lifestyles, the livelihoods, the ecosystems that are up there. So we are working with them, and Jacob Pantling, a PhD student from the University of Cambridge, accompanied Realize in this winter up into a region called Cambridge Bay, and we're looking at the possibility of going back next winter to do a slightly larger experiment and with more detailed measurement equipment to look at the exact profile of the ice that's been formed when you pump seawater through the snow.
Just the, you know, the science research and the engineering. You know, that's one of the challenges with as the research on methane oxidation continues. You know, what are the potential delivery vehicles for this? In terms of what we've just been talking about, have you done any, or has research been done about the viability? I mean, the scale that would be needed for it to be effective. What methods of achieving that mechanically has that been looked at?
So, beyond the conceptual stage, one does need to look at, well, the ramifications in terms of scaling this up. The initial work suggested that something like 10 million pumps would be needed to tackle, let's say, 10% of the Arctic. Now, those are both very big numbers, but they're not asking for the moon on a stick. These are things that, from an engineering point of view, that we could tackle. That said, we are looking at ways that we can reduce the number of individual pumps, for example, that will be needed. And that's the first idea of flooding the snow, because at any particular location, you wouldn't leave the pump in place for very long. You'd do some snow flooding, and then you'd remove it and move somewhere else. And that would reduce the number of pumps that you would need to tackle, let's say, 10% of the Arctic considerably. The second thing is, well, how do you organise the logistics, and what kind of technology would be needed in order to access that amount of the Arctic in a mobile fashion? And the initial thinking is that the access will be from underneath the ice rather than from on top of the ice. Things are a lot quieter underneath the ice than they are above the ice in the Arctic winter. And then the last issue is to do with the energy source, because the last thing we want to do is just to use this and have yet more fossil fuels being burnt to provide the energy to drive the pumps. And therefore, looking at technologies such as wind power in the Arctic winter to go and drive the energy, and then how is that going to be carried, let's say, by underwater drones? Is that going to be in the form of batteries, or will it be in the form of hydrogen fuel cells? The work that was undertaken this winter was looking at was using hydrogen fuel cells, and that was part of the testing, just to find out whether these would work in such harsh conditions.
So a lot of this is just mechanics and multiplication in a way. It's not that you're looking for an exotic thing that you don't know exists. I mean, the elements seem to be basically there.
Well, one of the elegant things about this, and as an engineer, I like to look at other parts of society where people have already done amazing innovation, and can we go and learn from those, beg, borrow, steal from those, and apply them in different contexts? Because a lot of the engineering work would have been done already in these areas. And the idea about pumping seawater on top of sea ice, when you're only asking to pump the seawater 1 or 2 meters, so you're not lifting it very far, it's using technology that already is used elsewhere in industry and in harsh environments, but this time with a slightly different application. And that, I think, is a sort of where we are with climate change, is trying to learn about sort of innovations and technologies elsewhere in society, and what could we use that for, rather than always starting with a blank piece of paper and saying we've got to start from scratch. No, it's much better, I think, to try and look at what we've already developed and seeing whether we can either tweak it or even directly apply it to new applications.
So on a personal level, how do you feel about where we are? Because, I mean, you know, the science is obviously important, but there's so much more than science to, you know, that's going to decide whether we make it through all this or not.
Well, I'm an optimist, so I think we can navigate our way out of this. Whether we will navigate our way out of this, that's way beyond Shaun Fitzgerald to decide. This is something that wider society needs to decide, whether we're going to really go and make a difference. And that does cause me concern, only because largely, look at the last 30, 40 years, when we've known that burning fossil fuels is the wrong thing, and no matter how hard we've been talking about it, we have still just continued to increase the rate at which we are releasing carbon dioxide to the atmosphere. So we've known it's the wrong thing, and yet we're on the black oil fix, as it were, and that, therefore, is the thing that causes me concern. Even though we might have the right answers, is it the will of society at large to actually use those?
That's great. Thanks. Okay, I think that pretty well covers most.
Cool. Do you want to do anything outside?